All right, good morning, everybody. Welcome to our second week. We are in the second week on online sessions, and happy Friday to all of you. It's been 10:10 and I'm watching the people are coming in. So we'll get started today. And as I have been doing so far, we will start by having a warm-up question, and that will be a good way for others to join. And I have been trying to type it up so that I don't get distracted while typing it, and so I'll send it soon. But what I have done last time, we had a question about genres on music, and I will keep my word, and we are going to think about whether that is going to be something that we can relate it to decidable problems on Turing machines, which is the subject we are we're discussing. But that was about music, and today I want to ask you about writing. So that same genre concept could be used for literature, for writing or reading. And so you know how your tastes are. So I'm going to ask you this question. What is your favorite literature or writing genre? Last time when I asked this question about music, I got challenged. There were so many things that I didn't know that what they were. So I'm going to make my life easier today and ask you to give me 1 or 5. I know you're very sophisticated people, and so you will come and tell me kind of very specific things. But let me go tell you what the options are. Mystery, thriller, romance, fantasy, science fiction. I've got 5. If you want to be more specific, then you could write in parentheses what one of these 5 yours is. But this is the category I have. And so go ahead and start doing this. And let me actually go where I want to go. I'm not going in the right place, I know. You have heard me the question, but I want to be here where the question actually is. No, okay. I'm struggling to get to, you know my question, I'm going to get there. Going to get to chat so that my window could get there. Right, okay, now I have managed. Okay. And we'll give people a little bit of time to type this one up before we get started with today's discussion. Right. And it will be a single question today. We'll get right to our topic for the day right after this one. And while you type that one up, some of you have been extremely fast in responding to the survey I had yesterday. I want to see how the recordings are coming and how the lectures are working for you. And some of it was posted just yesterday, but I wanted them as quickly as possible. So those of you who have not had a chance, make sure that after the lecture is done today to just quickly go through that survey. This is a Qualtrics survey that talks about how you're experiencing, how the lectures are going, the speed, and all things around it, and also about the recordings. And I also want your input on the final. As I have told you, it's going to be take home, but I want to know what kind of other things you have in terms of other finals. And so make sure to go there and complete that survey. All right, looks like people have got a chance to weigh in on today's question or map question, and so we can get started. Decidability is what we are discussing, and we are in chapter 4 in the book, and we did start last time to talk about so we'll have 2 things, right? We will have things that are decidable, things that Turing machines can decide, and things that are not decidable. And so we will devote an entire chapter, the book does, and we'll learn techniques to show undecidable language, and that will be the subject for our discussion next week. But what we've started doing last time was look at decidable language, and we will know them that they are decidable, and we have been going through them carefully to show that they are. And so I have titled it Decidable Language, what we did last time and what we will do today, except that we'll just get a little bit of a teaser into what an undecidable language may look like. But otherwise, both last week's last lectures, that was Wednesday, and today's discussion will be around decidable language. And we kind of grouped them into two. The first category was language that we have treated in the beginning of the semester, where we looked at finite automata and their equivalent way of looking at them in terms of regular expressions. And so those languages were regular language. So I saw a number of things. We saw a number of things, and I told you that we'll be counting, and so there were different results we show for decidable language problems that we formulated and showed to be decidable. One had to do with acceptance, and we saw 3 variations of them. Given a DFA, does it recognize this language, that acceptance, does it accept it and formulate it in the form of a decision problem, a membership problem, and then we saw how that would look like when it's an NFA, how that would look like when it is a regular expression. So in other words, on that first point there, we saw 3 variations of problems. And then we saw emptiness, and we proved the result, and so there were 4. And we wanted to talk about equivalence, and the slide, when the lecture was ended, I left you with a slide, but I didn't discuss it, and so that's what I will pick today. So we saw 4, and so there is a 5th one that would come. That was about finite automata and regular language. What we will be doing today, in addition to finishing off that equivalence for finite automata and regular language, that decision problem about equivalence of 2 languages, we will be looking at decision problems, decidability problems concerning context-free grammars. And just to match up with that parallel I have shown you for finite automata, for context-free grammars, we have the language is context-free language. And so we'll see 2, generation and emptiness, just like what we had done in terms of acceptance and emptiness for finite automata, for regular language. We will see whether these are going to be decidable in terms of context-free grammars in language. The equivalence one is the place where you will get to see, as I said, an appetizer for when a problem is undecidable. So if you hate spoilers, I have given you a spoiler alert right now that there will be one problem we will see is now going to be decidable, but we will actually show that next week, but the other things will be more around decidable. So the discussion will be to determine, to show that and prove them, and we will see techniques along the way. So we begin by number 5 today, because we've seen 4 last time. And so we are in the realm of finite automata, regular language, and what we are going to determine is going to see whether this particular language is going to be decidable, if we can have a Turing machine that decides it. And just like what we've been building last time, and I want you to be more comfortable now with how we denote these problems, this language, we're going to be using a word, a letter or 2 letters that would kind of give us a hint on what problem we're looking at. And this one is about equivalence. So that's what the EQ is there, and we're working with a DFA. And so we have 2 language DFAs, A and B, and we have their corresponding language, like the language of A and the language of B. And what we are interested in showing is that they are equivalent. So I'm going to follow what I have been doing last time. I'm going to state the result first, and then what we're going to be doing later on will be to prove it. And I'll give you time to kind of write notes and kind of carefully explain, even though we have a lot of things on one slide. In this particular slide, we only have one thing. Let me take you way, way, way back to right before spring break. And that was where we discussed, over Zoom, in fact, where we discussed the table filling algorithm. And if I would not expect you to remember, but the first 2 slides there begin by saying, well, why would we would need to talk about 2 equivalences? Why we would need to talk about whether 2 DFS are equivalent? Okay, the goal there was to say, I may have multiple DFAs, They may be equivalent. They're doing the same thing. The languages are the same. But the goal there with that table filling algorithm was to find what would be the minimum one to represent it. That was the goal, and that was what we did. But the idea along the way was to show that the two languages are equivalent. So we're not seeing this for the first time. We saw it then, and we motivated it that way. And so we're going to be now seeing how we can do this. And as I have a couple times told you now, the proofs that we will see, how we will show this is a theorem, we're not going to prove it, is going to be a way constructive. And so we'll look at, we're going to bring this Turing machine that's going to do this job for us. But I want you to remember that we are talking about equivalence of two languages. In this case, a language of one DFA and a language of another DFA. And we have said already that it is decidable. That means our task now is to go get that Turing machine that will do this decision, that will decide this. Proof. So now we're going to have a few things. And so be ready. And so if you see some compact, dense, really written things, I just wanted to help you. You can go back in the book and read this, but don't be scared. So this is a proof technique now. A proof technique that will be constructed, will have an algorithm at the end of the day, but we are going to do things differently in a way that is not something that the problem itself would give us. So we want to show two things are equivalent or equal, let's say. And these are, for our purposes, we can think of them as sets. And so if two sets are equal, one way to do it, to show that they are equal, would be for you to say, I'm going to go get one element from this set. And I'm going to look for that element in this other set and make sure that it exists there. And so I mark it somehow. And then I have looked at this. And then I take another element of this set. I look at them and make sure that, it exists there and it doesn't. And then I mark that I have found it. And I go about doing something like this. And then I finish these elements and then I make sure that they were found there. The moment I find it's not existing in this other one, then I can say they will not, there is no way they would be equivalent. You can begin to imagine that this is going to be a tedious and not necessarily an effective way of doing it, but there's lots of things that set theory and things like that that we know from before that could help us. And here is a very, very nice place where you can see, we're going to prove this, which is what we are tasked with, but there is also something more that's happening here. And so we're going to kind of work with set theory, things that would help us have tricks in a way. So to prove this theorem, we're going to use the theorem about emptiness, and we saw that last week. So we have an FA, and whether that one is empty or not, we decide. That's decidable, and we showed how to do that. And so we are equipped with at least one thing. We know when a set is empty. So we're going to use that theorem, and we're going to construct now a new DFA, and we'll call it C, and we're going to get this one from A and B, where C is going to accept on one condition, only those strings that are accepted by either A or B, but not both. Okay, we are headed towards showing that A and B are equal, they're equivalent. And I've come up with a C, a new one, that's going to do one job. And the job that C is going to do now is it is going to accept those strings that are accepted by either A or B, but not by both. If A and B were actually equal, then C doesn't have any chance to see anything, but because there isn't that a string that is accepted by either A or B, but not by both. There isn't such a thing, and therefore C will be empty if they are equal. So if A and B are recognize the same language, C will accept nothing, it will be empty. The language LC, the way I have described it now, when you accept or when you take something, when you have two states and you're taking from this or from this, but not from both, is called symmetric difference between the two. So when I have two states and I take the intersection, it means the thing that's common to both. The thing that is outside of that one is called the symmetric difference. And here is a picture for a symmetric difference. So we have got the language of A on the left, the language of B on the right. You see the intersection, that's the white one. That would have been in the intersection, but we are looking at the symmetric difference. And that means the one that is outside of that one. And if these two are indeed equivalent, then that would be empty. So they would collapse, LA and LB would collapse. I have that purplish note there, which shows how I am denoting complements. So the symmetric difference between two sets, C, between two sets A and B, is written in this way. You've got the intersection of A and B, the intersection of A and B complement, all of A except what is contained in B, or what is in B except what is contained in A. In other words, A intersection B complement, that's one, union A complement intersection B, this thing together is called the symmetric difference. So the C that we're after now is going to be the symmetric difference between A and B, and that's what the picture shows you. Okay, because I know when to know when a set is empty using the in finite automata, and I have constructed a way now to convert the question I was asked about the equivalence between A and B into turning it into another set C that is going to be empty whenever these are equivalent, whenever they are equal. So now my task will be to decide C. And thanks to what we learned on Wednesday, we know how to do that. And so that will be the algorithm I'll show you now. And that's what you see on the right. So my DFA now is going to be called F, and it's taking two A and B, the two DFAs, where A and B are the two DFAs. And so we're going to construct a new DFA C, as I just described now. And then we're going to run a Turing machine from the theorem we saw. This theorem 4.4 was a theorem from Wednesday. And what does it do? It tells me that a DFA is, the E there is empty. Where empty set of a DFA is a decidable language. That's what we learned from last lecture. And so we run that one. And if it accepts, we accept. If it rejects, we reject. So we just proved this slide was up there when I posted it on Ozbol. We did not go through it last time, but this one was the last problem in the class of regular language and finite automata, where we are showing whether something is decidable or not decidable. So for now we know that when we have two DFAs, A and B, deciding whether they are equivalent is decidable. The question of whether they are equivalent is decidable, and we just constructed very beautifully a Turing machine, we called it F, that does this one, that kind of pulls out a trick from set theory that uses symmetric difference to express equivalence in a slightly indirect way. And so they are equivalent when these two things collapse, and the white is all that is there and the gray part is absent in the picture. And now that the set is empty, can be seen with what we constructed, the Turing machine we constructed last time. Now we have established one more result. Okay, so we move on now. We move on to context-free grammars. And so we're going to walk through very similar things, except now we know we are working with grammars. And so the first thing we want to do, just like we had acceptance for finite automata and regular expressions, so we're looking at a DFA or an NFA or a regular expression, and we had an input string, and the question was does this accept it? Now we are going to turn the question in the form of a context-free grammar. And so we're going to say, G is a context-free grammar that generates W, and I've got a language defined like this. Is this language decidable? Is the question, generation. So can this grammar generate this string, and we have a language around it now. And so we begin with the result, and then we'll work with the proof. This is the way I have built up these slides, and now you've understood how this one is working. And so we are going to go look at the proof for this one, or the Turing machine that we would construct for this one. Anytime you have a question, you should unmute yourself and ask me or say something. And so all I see now is very enthusiastic answers to your warm-up questions. But other than that, it looks like you're following along. So I'll just continue. And so this language is decidable, and we're going to prove. I'm going to have a couple cases today where we will, which is nice. As a student, I used to like these things when they show me something that doesn't work, because that's the first idea that comes to your mind, and then you can see how that was faulty or what was wrong with it, and then you get the right idea. And so that tells me that these people who are writing these books or papers or whatever it is are humans. So there's something that came to their mind first that didn't work. And this is how life is in general. We not always get the right ideas the first time. So for that reason, I will demonstrate it. The book does it. I'm not coming up with it, but the book does it, and I like that. And so I'm going to show you first an idea that doesn't work, and then we'll get to that's why you see idea 1 here, and they will have only 2, one that doesn't work, one that works. Okay, another spoiler alert here on how many we are expecting. So for a context-free grammar G and string W, we want to determine whether G generates W. That's what our task is. That's what the results say. This one is decidable. And so our first idea is to use G to go through all the derivations to determine whether any is a derivative of W. Remember what grammars were doing. I know it's been a while, but you know what grammars were doing. You've got a start variable and you've got things, rules. And so if you wanted to know whether a string could be derived from it, you'll have to work through it, right? To apply those rules, you could use a leftmost derivation or rightmost derivation. But you do that and then see if that grammar generates this language. And so the first idea is go get G to go through all the derivations to determine whether any is a derivative of W, this string that we are working with. There's a problem with this already, and it's because we've got infinitely many derivations may have to be tried to determine whether this one is going to be there. And so if G does not generate W, this algorithm will never hold because it has got infinitely many things. And so this idea is fine to be a recognizer. It's a Turing recognizer, and you know the distinction between a recognizer and a decider, but it is not going to decide, which is what we want. And therefore we need another idea. Try everything is basically what it was. And at least we reminded ourselves that there are infinitely many derivations that may be had here. And therefore we need to reduce this, get things that are finite. And that would be the second idea. And so we want to turn this Turing machine that is a recognizer but not a decider into a decider so it does what we want it to do. So the second idea will be to ensure that the algorithm now relies on finitely many derivations. I'm going to stop here for a second and take you back to a place where we had something that we did not necessarily say it this way, but would be a very good place where its use is going to be demonstrated. And that is about CNFs, or Chomsky normal form. If I know that a grammar G is in Chomsky normal form, then any derivation of a string has 2n-1 steps where n is the length of W. So W is my strings. We did not show this in class, by the way. In the book, it's an exercise, and for now, it's enough to just say it's a way to reduce it to finite steps, but you could, I'll try to encourage you to do it, but you can show it's not very difficult, and maybe I'll just show out how to do this, to show this is actually true in one of the, in opportunities we have to work through in another example. But for now, it's enough. So if I have a grammar G and it is in Chomsky normal form, any derivation of this W has 2n-1 steps. And it's not very surprising that it depends on the length of that. And you know what the length of a string is. So how many things you have in it. And so that 2n-1 is how many derivations you will have. So the function or the point I wanted to make is there is this practical use with having to turn a grammar into Chomsky normal form. If we do that, then we have this many derivations, and we can then check only derivations of this many steps to determine whether G generates W would be sufficient. Instead of having now to work with infinitely many, we have now reduced it to a finite number that only depends on the length of of W, the string we have, and this is how many we need to check. That means now we have a clue. We have a clue how to go about this one in a way that will be useful, and that will turn the Turing machine that we are about to design from being just a recognizer into a decider, because it's going to hold. There is only a finite number of steps to go, and that finite number of steps happens to be 2n-1 derivations. So we can convert now the grammar G into CNF by using a procedure we have discussed. And I wanted to remind you where this one was. And so I went back to our old note, the way we were doing before we got things online. And so this is a picture I took from the scans I had to post on Oswald every time we end up after a lecture. So this was actually a lecture that happened on February 19. And so if you go look at the last 3 or 4 pages of that slide, you would see how the conversion would go. I know you know this. I know you know now how to convert a grammar into CNF. We saw this in class, then we have example 210 in the book. That's what the class, by the way, does. But also we revisited this procedure. And that's the reason why I have done it a couple times also. You just now have a very good example for seeing why converting to CNF has got, now it's going to help us prove this result that the CFG problem, this problem that we are trying to decide is a decidable problem. I also wanted to make another case. I just didn't want to remind you here about when that lecture was for you to go back and look if you have not been very comfortable. I'm almost sure that everybody now is comfortable converting a grammar into CNF. But what you see from this discussion now is one place where it is used. And so we have done a couple places where exercises where you have done this one. But I also wanted to defend myself. So if you ask James, he would tell me, he had said it several times, my handwriting is horrible. And so I wanted to contend that, I want to challenge that. It's not that bad. And so now even on a small scale on this, you can see on this screen, and I'm sure it's not, I know I can write better than this, but it is not as bad as James makes it sound like. All right, that was the other purpose of this slide. I wanted to have documentation that it is not very bad. Okay, so now the complete proof, after we have work it into, turn it, or we have found a way to limit the steps we need to do, and that's to turn it into CNF. This will be the full description, idea 2 when it is fully described. So we're going to now construct the Turing machine, and this time we'll call that Turing machine S for this language. For a set of language where we are going to have a context-free grammar G, and does it generate this one? That is what the CFG would stands for. So on input G, where it is a context-free grammar and W is a string, the first step out of our Turing machine would be to convert the grammar into an equivalent grammar in Chomsky normal form. Then, because it's in Chomsky normal form, we know how many steps we need. We can list all derivations with 2n-1 steps, where n is the length of W, and then we're going to work, except a little minor detail here. When n is 0, that number would probably look weird. And so n equal to 0 is a special case. We then want to have all the derivation in one step. So let's take that one out. And so we have in general this statement that says we have this many steps to check. And if any of these derivations, now we have, instead of having infinitely many things to check, if any of these derivations now generate W, we accept. If not, we reject. And that would be a complete description of our Turing machine that decides this particular language. I've got a side note there, and maybe let me spend 30 seconds talking about this one. And this one is for those of you who probably would always want to see where these things are applied. Most of the lectures we had before spring break, every time I have an example, I would always mention compiling programming language. And the reason for it is because they are so very frequently used there. And so to determine whether a context-free grammar generates a particular string, which what we are now saying, when I look at them, these problems now, we call them 1, 2, 3, 4, 5, 6, and we go around that one. If you were to pick this, when they may look like you are, following a pattern and you are generating this and you're doing that, and they may sound a little bit artificial sometimes to you. They're not. But this in particular has got a huge implication. What you're really doing now, when you are trying to decide whether a string can be generated by a context-free grammar, when you do that, what you really are doing is what compilers do when they have a program written in a certain programming language. They're saying, is this acceptable? Am I going to, tell the person who wrote this program, no, this is not compiled. You've got this error, they've got that error, you get this message. And after it is successfully compiled, then it is going to run. So what the programming language compilers are doing is to do a CFG. They're deciding that. They're trying to say, if I have this grammar, which is what a programming language has, by the way, it could be lengthy, but it is a grammar. This is how things would be. That's how your if and then and else would do. That's what your while block will do. That's what your for statements would do. That's what an assignment would do. You can have a complete description of the grammar for that programming language. It's only then, actually, that a programming language could have a compiler written. So this problem that we just start looking at is hugely important, that it is related to the problem of compiling programming languages. Now, okay, this was maybe one of the two big points I want to make. One, hugely important problem, directly used in construction of compilers. But then this little algorithm that we have in green box there is not how real compilers would do the job. They want to recognize, that's what compilers would do, but they would have a better way of doing this one. This one was, we're not interested, at least for the next couple of weeks, until we get to a point where I will tell you we care about efficiency. We're not caring about efficiency so far. We're saying decidable, we're saying recognizable, and that's it. And we present a Turing machine. We never cared whether we could have a better algorithm for it. That's a different question. And so this particular case, I want you to notice, if you were to open up a compiler now, C, for example, a C compiler, they would have a generator for this. They would have an algorithm that would do this. They will not formulate it in the form of a Turing machine, but they would have. But if you were to think about what that algorithm is doing, it is not going to be like this. It's not going to be about Chomsky normal form and have 2n-1 steps and checking it. There are much better ways of doing this, more efficient ways of doing this. But that is not our purpose. We will have complexity theory is the subject there. When you care about how much time, how much space an algorithm takes. That's the third part of this book, which is not really what this course is about. So we don't get there, but we'll have a lecture or two to just have a flavor of that one. And those problems that are efficient have got a name. And those are called polynomial algorithms. This is not a polynomial algorithm. We'll just at least say that there is a way for doing this one in a better way. That was the side note there. Okay, and it is enough. Okay, so if you are a big fan of PDAs, okay, what are they doing? They are push-down automata. They were the ones that took care of what context-free grammars would do. So regular language, we had NFA and DFA, and they're equivalently expressed with regular expressions. So if I take that regular expression counterpart in context-free grammars, it will be the grammars. And so we need something that was, where are our NFAs and DFAs? And that's where PDAs came. And you remember them. You remember them very well. And so they had a stack on the side, and they had to remember, and things like that. So because we have a result that says everything that could be a context-free grammar could also be expressed using push-down automata, any statement now that we are making around context-free grammars would apply to push-down automata, because we have seen this. And I have pulled out my notes again there, and we discussed this one on February 24. So if you take me to court and you say you didn't cover this one, I have an evidence. On February 24, we discussed push-down automata, and there was a term, a book called Theorem 220, that talks about that when a language is context-free, if and only if some push-down automata recognizes it. And we saw both directions. In fact, one of the directions we devoted an entire lecture, and the other direction we devoted another lecture. So what we did there was to show this equivalence. So that means now, although they have not been coming up in this form, anything that we make about decidability problems around context-free grammars would apply to push-down automata. And so that was the reminder on what you see on the right. Okay, I'm going to continue and work with context-free grammars, and we're going to work with one more. So we talked about generation. So go back a little bit in your mind and see what we were trying to do with context-free grammars. What was one was generation, emptiness, and the third one was equivalence. We have not yet arrived at equivalence, so we are now on that emptiness test. And just like what we did with regular language, we are going to see whether this language is decidable or not. What's our language? Because it deals with emptiness, we'll call it E, and we're working with context-free grammars, we'll have that subscript CFG. So we've got a G, that's our input, it's encoded, it's a context-free grammar, and we wanted to know if the language of this grammar is empty. And so check for emptiness. We did successfully when it was DFA. Can we do it when it is context-free grammar. And the result is going to be what we'll see in the next one. Just like what we had before, we are going to have a bad idea or an idea that's not fully baked, something that will not take us very far, and then we'll refine it and look at a good idea. Okay, so what about we just use what we just had? There was a Turing machine we just constructed that would very nicely, okay, we acknowledge that it was not efficient, and then people who design compilers would know better and they would do, but we were able to see when a language generates something, and we know how to do that. We spend all this time, you know, doing it. Can we use it? And we could, if we are going to live with one big problem. So the result that we just had now to test whether a context-free grammar generates some particular language is what our Turing machine S did to do. And to determine whether the language is empty, the algorithm may try going through all possible W's, one by one, and then see it didn't generate this, it didn't generate this, it didn't generate this, and therefore we say it's empty. But there are infinitely many strings that we'll have to try, and this method could be running up forever because the input string now W will be the one that bring up this issue of having infinitely many things to try. And so it was good of us that we tried to reuse what we just did in the previous case, because we now know how to decide whether something can be generated. Can I try everything? Can I try all possible strings? And then say when none of them, you know, there isn't anything, then the language must be empty. That one will not work because it will have. So we need a different approach. And that would be what we will call idea 2. So to determine whether a language of a grammar is empty, we need to test whether the start variable can generate a string of terminals. Now, this is where a place where you would probably also want to remind yourselves about how a grammar does. We've got two things, right? We've got variables and we've got terminals, and anything that will be further explained in terms of having some other thing is a variable, and anything that is an input is what the terminals are, and the things that we would write in to go from variable to another variable or to terminal would be called the rules. That's how things work. So to determine whether the language of a grammar is empty, we need to test whether the start variable can generate a string of terminals. Okay, the algorithm now will do this, but it will do so. So we are on our way to devise a better idea. That's what our idea 2 is. And so we say how we are going to be testing it. We are going to see, can I start from the start variable, and whether it can generate a string of terminals is what I am going to do. And so for this one, we're going to achieve this, but we're going to achieve it by solving a more general problem, not just the start variable, whether it generates terminals, but a more general problem. And that more general problem is going to be done for each variable, not the start variable only, but for each variable, whether the variable is capable of generating some string of terminals. So you may want to spend 10 seconds trying to see what the point I'm trying to make. So the first one said the obvious thing. Can I start from where I should begin, which is the start variable, and generate a string of terminals? That's what I want to show. This is my better way, the better approach, instead of having to try all possible inputs and the language empty. Instead of doing that, I'm going to try now to see if the language of the grammar, the start variable, can generate a string of terminals. Now I'm going to come up with an algorithm, but I have generalized it to say not just for the start variable, but for each variable, whether the variable is capable of generating string. I want to come up with this one. And I'll show you in the next slide, and I will talk about the fourth point there and elaborate on this one. But I want to pause for a second and remind you how you do when you write programs. And this is probably something that you would immediately say, yes, I have done that so very many times. Let's say you've got a problem and you're trying to work out how your algorithm is. Most of the time, it's not necessarily clear how you would go about it. Maybe it's got different pieces and things like that. But when you start working out, you would recognize that there was a portion of your code that looked like could be a function. Could be a function on its own. If only you could have it, conceptualize something that you could abstract it so that you could say, if I give it this input, and it will generate this output. For example, in the course of doing something, I might have needed to do some summations over a sequence of things, right? I observed that I needed to go through a table or an array or something, and I needed to add. And so if this has come a couple of times, then you would say, I think I should add something that's called sum. And that sum will take, the start and end of a table, and then it will give me an addition. So that's a routine or a function or whatever. And sometimes it may come very naturally for those of you who are very good and things like that. Otherwise, it may come along the way as you work through that you identify. That's what is happening here in a way. So if you start from the start variable and you have a way to mark them to generate whether you can get terminals, and I know these rules in my grammar have got also variables. The only distinction is the first one is the one I cared about, whether this is going to generate. I could apply a routine now, something that could be used by the start variable, but it will apply for each variable. So that's what the fourth point is trying to say. When the algorithm has determined that a variable can generate some string of terminals, the algorithm keeps track of this information by placing a mark on that variable. So for that, because I have worked with this one for each variable, when that variable is able to generate some string, I will say I'll give it a pass, so that will get it. And so we would mark, and if we say this one would go all the way to the start variable, then we would say the language would generate it. That's what it means. So this better idea, first the algorithm marks all the terminal symbols in the grammar, because that's where the end is in a way. We're working our ways back. All the terminal symbols in the grammar, and then it scans all the rules of the grammar. And if it ever finds a rule that permits some variable to be replaced by some string of symbols, all of which are marked, then the algorithm knows that this variable can be marked too. So it will apply this one. So the algorithm continues in this way until it cannot mark any additional variable. So try to understand what has just happened. So we could just mark the terminals because that is eventually when we decide, we would say the grammar has generated this string is what we input symbols is what we would say. And so we mark them because they are terminals, and then we scan the rules of the grammar. And if we ever find a rule that permits some variable to be replaced by some string of symbols, which are already marked, then the algorithm knows that this variable can be marked. It passed the test, is returning. And so when the algorithm continues in this way until it cannot mark any additional variable, then it will terminate. So this is more like a verbal word description of what this better idea of ours is. And I'm going to have it now put in a more formal way, and we'll give a name for that Turing machine. And S was our Turing machine. We keep calling these Turing machines. We give them names. And so to just show that they are different, and actually the name of an algorithm now is what it would mean. So the Turing machine R that implements what we just went through in the previous two slides, it looks like this. So I have R, the name of our Turing machine, which is going to decide for us whether that language generated. So and so we have on input G, where G is a context-free grammar. We are going to do just what we said in words in the previous slide. So we are going to mark all terminal symbols in the grammar, and we're going to repeat the second stage until no new variable gets marked. And this is where the subroutine, this is where I told you now it has been formulated in the form of a function, something that could be generalized. That means that we can apply for all rules, not just starting from the start symbol. So that's what's happening in step 3. Your function call, your routine. If you speak Java, maybe it's called something else there. So mark any variable A where G has a rule like this. A goes to U1, U2, UK. And for each symbol U1 to UK has already been marked when it is marked. So you do this. So after this is completed, if the start variable is not marked, then we accept. Otherwise, we reject. And so that will be the end of our proof for what we were looking for. Okay, I am going to, we've got 5 minutes, and so we're going to have the 1 or 2 problems that are left for us to do, and equivalence was one of them, and I want to finish them. So I'm going to go right ahead into that one, and I'm hoping that you are following me. So equivalence is what we want to see. When it was DFAs, we have 2, A and B, to determine whether they were equivalent. was something decidable, and we used the, that symmetric difference and things like that. And so we will be tempted now to say, if I have two grammars, G and H, whether they are equivalent or not, whether this is decidable, is the question we want to ask. And this is the place where I gave you a heads up that this is probably not going to be decidable, and we'll answer it for sure now. We'll show the results, how to prove it next time, but let's consider what we would do. We saw an algorithm that decides this analogous one with equivalence for DFAs, for finite automata. And what we used there was this decision procedure for emptiness to prove that, whether this one was decidable. Could we then, because this decidable emptiness is also decidable in the context of context-free, it's funny, in the context of context-free grammars, the emptiness is also decidable. Can we just use similar idea, like the symmetric difference there, to show this? And we will be disappointed this won't work, because we relied on complementation and intersection in the proof for the equivalence in DFAs, because complementation and intersection was something that the language was closed under. But that's not the case. And you may remember this one from a discussion we had in class some time back. Context-free languages are not closed under complementation. Context-free languages are not closed under intersection. And therefore, we cannot use that trick. And in fact, this language, whether two grammars, G and H, are equivalent, is not decidable. A Turing machine cannot do that. And so we have a result. For the first time in the discussion, both on Wednesday and today, we saw a problem that is not decidable. Two context-free grammars, G and H, are they equivalent? That is not decidable. And we will need more machinery to prove this rigorously, or to show this, and we have not come there. That will be the subject for next week. But I want to finish off today's discussion by looking at context-free language generally. Context-free language, you remember them, what they are. And we have a big result that says every context-free language, whether two context-free languages are equivalent, is not decidable. But every context-free language is decidable. And so the idea, and we're going to finish off this, and if you feel like I'm going to go a little bit faster on this, you will understand. But it is not actually difficult to show this. So what do we want to do? If A is a context-free language, our goal is to show that A is decidable. That's what the theorem is saying. So we'll do two ideas like what we have been doing today. For all the theorems that we have proved, we had an idea that didn't work, and we showed an idea that would work. We will do that for this one also, except that I'll do it in one slide. The idea that doesn't work is going to come in one slide. So the idea that doesn't work is going to take us back to what the machines for context-free grammars were, which is PDAs. They are push-down automata. And so can we just convert it into a Turing machine? Because then that way we could say we will be decidable. And this will be the Turing machine, and if you compare them with push-down automata, Turing machines are more powerful. They have got a more versatile tape. And so it's not very hard to do the simulation of what the stack, this additional memory of a push-down automata would do. That gadget is not difficult. We can do that. And the PDA may be non-deterministic, but that's not a problem either. We can turn our Turing machines also to be a not deterministic one. And we have learned last week that Turing machines are equivalence between deterministic and non-deterministic, and so we will not have any problem. Anything that we have been doing so far with deterministic Turing machines will help us get there, even though the Turing machine is not deterministic. So that would not have been a problem. But there is one problem. There is one difficulty in going around with this route of trying to take a PDA for this language and turn it into a Turing machine. And that difficulty is because some branches of the push-down automata may be just going on forever, reading and writing into the stack without ever halting. And so if we were to simulate this push-down automata, then our Turing machine is a recognizer, but it will not be a decider. And therefore, we need another idea, much like what we had done before. And so our better idea is to use a Turing machine, and we'll call it S, that we designed to do the context-free generation. And we had done this in the beginning of the lecture. We had shown the language, we called it A, and that was about acceptance. And we had the context-free grammar G, and so does it accept it? We worked through it and we saw how to prove it. And so we're going to use that one, except that we're going to have a copy of it now. So we need two. So our proof now will be, we have got a grammar, and it's a context-free grammar for this language A, and we're going to use a Turing machine, we'll call it MG, that decides A. So we're going to build a copy of this grammar into MG, and it works as follows. We have got the input, that's about generation now, it's about acceptance. We run our Turing machine that we proved, that decides, that accepts this one. So if it is accepted, we accept it. If it is not accepted, we reject. If it is rejected, we reject it. So it may look like we are kind of not doing very much, but we are technically successfully using whatever it is that we used for acceptance or generation into showing that context-free language is decidable. So I have finished, and this is a very nice picture of the language we've been seeing so far. The containment. We've seen these variations of these pictures, but it is a nice way to show it. So the result we just proved now ties all the four classes of language we have been seeing them, and this is our world. This is what the language look like when they are contained in one another. All right, I hope you have been following me. It's 11, and I know you have classes to go to. I will stop here. If there is anybody who has got a quick question, I can answer. If not, we also always have follow up on Oswald that you can ask. The homework 6 is due today. I know a good number of you have already submitted. If you have not worked, James will be very happy to answer your questions by email. He didn't see a lot of visitors the last time. I told him this may be because they just have full control of what Turing machines are, so they probably didn't need help. But if you need help, if you've got questions, make sure to ask. I will see you otherwise on Monday, and have a very good weekend.